Hi all. This brief announcement is about memory-efficient, massively parallel algorithms for LCL problems on trees. This is joint work with Sebastian Brandt and Jara Uitto. I'll first define the local model, then I'll explain what is an LCL problem, and define the MPC model itself. Then I'll go over our main result, which is establishing the MPC complexity landscape on trees. And lastly, I will leave you with some open problems. So the local model, introduced by Linial in '87, is one of the most important models in distributed computing. In this model, we're given an input graph, which is also the communication graph, with n nodes and m edges. Initially, nodes only know their instant edges. In each communication round, which are all synchronous, nodes send unbounded size messages to each other via the edges that connect them. And the complexity measure of the model is the number of rounds until a solution is found. Algorithms are either deterministic or randomized, and in this work we focus on deterministic ones. So now that we know the local model, we can define an LCL problem. It is short for locally checkable labeling problem. Formally, it is a distributed graph problem on constant degree graphs in which a solution is globally feasible only if it is locally feasible in all constant radius neighborhoods. And examples include MIS, colorings, and maximal matching. So take coloring, for example. A node is colored with some color, then it checks its neighbors. If they are colored with a different color, then the solution is locally feasible for this node. And if the solution is locally feasible for all nodes, then well, it is globally feasible, so the coloring is proper. Problems that are not LCLs, for example, are MST and maximum matching. So for a node to know if the solution is a maximum matching, it has to know the whole graph, which is not possible in its constant radius neighborhood. So as you can see, LCLs capture many central problems in computer science, so naturally we want to know how fast can we solve them in, say, the local model. As it turns out, for trees, the complexity landscape is complete. And the way you read this is that all LCL problems fall into one of these complexity classes, so either constant, log star n, log n, or n to the power of 1 over some constant. And it has been shown that each of these classes are non-empty, and there are no problems between them, so the gaps are really there. And in fact, this rich line of work only recently came to an end when Brandt and others proved a complexity gap between small omega 1 and small o log star n. And we emphasize that this landscape is indeed for bounded degree trees and for the deterministic local model. So we understand everything about this particular landscape. So how about LCL problems in other models, like the MPC model? Well, let's first define the MPC model. It is fairly new, introduced in 2010. And here we again have an input graph with n nodes and m edges. But now the communication graph is fixed. It is the complete graph Kn, so that nodes can communicate in an all-to-all fashion. Again, initially nodes only know their instant edges of the input graph, and we proceed in synchronous rounds where nodes exchange messages, and the complexity measure is the number of rounds until a solution is found. In the sublinear variant of this MPC model, which we are interested in, we bound the memory of each node by n to the power of delta, for a small delta. And this naturally limits the total sent and received message size. We also keep track of the total memory use of all overall nodes, and we want it to be linear in the number of edges. And note that this restriction is the strictest possible, since it's barely enough to fit the input graph into memory. And again, algorithms are either deterministic or randomized, and we focus on the deterministic ones. So how fast can we solve the LCLs in the sublinear MPC model? Well, as it turns out, LCLs have not been systematically studied in the MPC model prior to this work. And we fixed that and established almost the whole complexity landscape for MPC. So we start with the constant complexity regime. Here we show that local constant time algorithms can be solved in constant time in MPC, which is quite trivial, as we can do pretty much anything a local algorithm can, since we work in trees of constant degree. But our mid-complexity regime is not trivial, as it solves local log n time problems in log n time in MPC, so an exponential speedup. Note here that we have skipped the log star in class, but we will come back to that later. So the mid-complexity regime, how do we do this? Well, we first take a look at the canonical algorithm of Chang and Petit that gave rise to the log n complexity class in the local model. And we do what they do exponentially faster. And here the greatest challenge was being memory efficient, as we only allow linear memory. Well, how about problems slower than log n time? So the right-hand side of the figure. It has a lot of complexity classes. And here we continue our exponential speedup trend and show that all of them can be solved in log n time. So we effectively show that all LCL problems can be solved in log n time. And for this result, we do not use any prior works, but rather we explicitly provide for any solvable LCL problem an algorithm with a runtime of log n. And our approach consists of three phases: rooting a tree, then processing the tree from leaves to root, and then from root to leaves. And in this talk, I'm going to show you how to do the first phase, so how to root a tree. The other are much more technical, but you'll get the general idea how to do them just by looking at tree rooting. So how do we root a tree? Well, the naive approach would be to start from leaves and orient their edges outwards, like this. Then remove them, because we don't need them anymore. Then start again, orient the edges, remove, orient, remove. And this way we find the root. And this seems even kind of fast until we take a look at the worst case, which is a path. And here, if we do the same steps as previously, then we do find the root, but it takes us a long time. In fact, it takes us ON time. And as it turns out, all of these three phases introduced previously have the same inherent problem, that if we only process leaves, then each of them takes ON time. So as a proof of concept, I'm going to show you how to perform this rooting phase in log n time. The other phases can be also done in log n time, but we won't be going into details about those. So we shouldn't exactly be surprised why only processing leaves does not work fast, since when processing leaves, we are not even using the all-to-all communication power of MPC. So hence, if we want something better, we should probably use global communication. So let's take a look at rooting a tree, but now we process leaves and paths at the same time. Why do we want to do this? Why do we also want to process paths? Well, a well-known graph theoretical fact is that at least half of the nodes in a tree are leaves or belong to paths. So by removing them in each iteration, this would result in a log n time algorithm. And this comes from if we remove a constant fraction of nodes in each iteration, well, the logarithm comes from that. And if removing them takes t time, this way would have a t log n time algorithm. So the question is, can t be a constant? Because if we want a log n time algorithm, it seems that we need t to be a constant. So let's take a look. Well, first, since leaves are just endpoints of paths of some length, maybe 1, it is enough to consider only removing paths. And there are two types of paths. Type 1 is either connected to a leaf, or type 2, the path is in the middle of the graph. And paths that are connected to a leaf, we want to orient and then remove. because we don't need them anymore. We know the orientation is going to be from the leaf outwards. But type 2 paths we want to compress, because we do not know the orientation yet. It can be to the left or to the right. So we want to create an edge between the endpoints, and we want to remove all the other nodes because we don't really need them. So can this be done in constant time? If you're a distributed person, you probably already guessed that no, you cannot do this in constant time. And that's the answer to our original question. Can t be a constant? No, it cannot be. So we have to do something smarter. Let's take a look at this kind of subgraph as an example. Here we have both types of paths, so let's take a look what happens to them. First, let's color all paths and their endpoints blue. And now we want each node to connect their neighbors with an edge, like this. So now let's identify the shortest possible path from one endpoint to another within each path. And then mark all nodes that do not belong to these shortest paths as gray, like this. And as you can see, these gray nodes are kind of useless in some sense and can be thought of as being removed. And by doing so, we remove half of the nodes on all paths. And now we do the same thing again. Each node connects their neighbors with an edge. And then we mark nodes that do not belong to the shortest paths gray and remove them. And by doing so, we again remove around half of the nodes in all paths. And then again, connect, mark with gray, remove. Now you can see that the path in the middle of the graph is compressed, as we want it to be, and the paths connected to a leaf become of length 1. So we can orient them in constant time and remove. So by this process, we remove around half of the nodes in paths in each step. And since you remember that half of the nodes, or around half, at least half of the nodes in the graph are either leaves or paths, we remove around 1/4 of the nodes in the graph in each step. So by this design / analysis, we get a log n time routing algorithm. Of course, I have omitted a lot of details, and the algorithm as such does not work. So the issues that must be resolved and are resolved in our paper are the following. During execution, new paths are created and all old ones may be extended. So what do we mean by this is that if we have a path in some iteration, then some nearby nodes may turn into degree 2 nodes. So they may extend the path. And this creates some issues that one has to deal with. Another problem is the memory issue, because as explained now, each node may need up to ON memory, which would break our linear global memory restriction. But all these issues can be resolved with careful design, which is exactly what we do in the paper. So now we have shown you that a tree can be rooted in log n time. And the other phases work similarly in log n time also, but they are much more technical. But after dealing with them in log n time, eventually we do get a log n time algorithm. And as you may have already forgotten, the problem we're solving in log n time was our high complexity regime. So we show that all LCL problems can be solved in log n time in MPC. So to summarize our results, this is the first systematic study of the MPC complexity landscape for LCL problems on trees. With our constant, mid, and high complexity regimes, we show that almost all LCL problems can be solved exponentially faster in the MPC model than in the local model. We emphasize that our algorithms are deterministic, and we use n to the power delta local memory and linear global memory, which is the strictest possible. So how about open questions? Well, as you remember, we skipped the log star in complexity class completely. So we pose it as an open question, as can it be solved, or can it be exponentially sped up to log star n? we strongly believe that it can. And this would actually complete the MPC complexity landscape with regards to upper bounds. Another interesting question would be if this exponential speedup can be achieved for general bounded or arbitrary degree graphs. Thank you for watching, and see you at disk.